In Lesson 21, we'll talk about probe selection for force curves, starting with the last slide of Lesson 20. And if you've been paying attention, in Lesson 16 I was talking about probe selection for imaging, and I said that cantilevers should be generally weak so that the forces between the tip and the sample damage neither the tip and the sample. But here we have discouraging news in the lower right. This force curve, its only useful information is the force of adhesion, the maximum negative force upon separation. We get no information about the mechanical properties because the cantilever is not stiff enough to indent the sample. And furthermore, there's very little information about surface forces because the cantilever is so weak. The instability, the jump, has made it miss much of the surface forces part of the force curve, the attractive part, the negative part. But before we go on and talk about what your best choices might be for a probe if you want to do force curves, there's one more thing I want to add to Lesson 20. I was talking about how the scanner position was represented by H, either scanner height or cantilever holder, and we used S as an offset for the sample surface. Now, if your configuration of your scanner is different and your sample is on the scanner, then your variable would be S and your offset would be H. And still you do want to take the difference between the deflection and the motion of the scanner. So you would just go like this, or this, depending on whether you want the positive direction to be into the sample or away from the sample. Before we talk about probe selection for force curves, let's talk about some related instruments and related measurements that might help make your probe selection easier. Back in the 1970s, there were some studies of the attractive regime, and these studies were done by something called the surface forces apparatus. And in that, you take two mica-coated cylinders of about a centimeter in diameter, and you bring them together and apart, much like a force curve in AFM. And for the most part, that was to study, as the name suggests, surface forces, and the point was not to indent, although occasionally you would study the deformed shape of those mica cylinders when the surfaces came into contact. And for decades, the repulsive regime has been studied, looking at the hardness of materials, so diamond tips poking into aluminum, for example, and leaving holes, and measuring the size of the holes, and looking at how much force was applied, coming up with a measure of the hardness of the material as a result. And then more recently, starting about the 80s, nano-indentation, where you monitor the force and the indentation depth instead of just one force and looking at the resulting area. And just to be clear, above the x-axis we have net repulsive forces, below the x-axis we have net attractive forces, and the regime of data that is new is here, where even though this is net attractive, we do have repulsive forces building up, and the atomic force microscope is the first instrument that is able to probe the first stages of contact. So this is very good for thin films and any application where the surface is very important. The reason why AFM has access to this part of the force curve and the other instruments do not, well, it has both great force sensitivity and a sharp tip. So the hardness tester and nano indenter, they typically don't have the force sensitivity, though they do have the sharp tip. And the surface forces apparatus does have good force sensitivity, but it has a very big tip and just does not indent to any significant degree. Concerning your choice of cantilever stiffness then, for force curves, if all you want to do is measure the adhesion between the tip and the sample, then it's better to stick with a weak cantilever. A weak cantilever is less likely to damage the tip or the sample. And there's another concern, and that is if your cantilever is stiffer than the interaction between its tip and the sample, there's a possibility that as you go up over bumps while you're imaging, the bumps will compress and you will not get accurate height information. So the stiffer the cantilever, the more probability that that might be true, as well as having a greater range of force, which might not be good for your sample if it's a delicate sample. If you're interested in this regime that's particular to AFM, the very early stages of contact, then you would want sort of a moderately stiff cantilever such that there are no instabilities on approach or retraction. But shortly after the forces become net repulsive, the curve becomes infinitely stiff. That just means the tip-sample interaction is much, much bigger than the stiffness of the cantilever. And so this distance is the maximum distance of indentation. It won't indent any further. And there you're fairly safe with the height information as long as you do your imaging at lower force where the tip-sample interaction is not so strong. And finally, if you want to start probing the bulk of the material, you need a very stiff cantilever such that up in the net repulsive part of the force curve, you still are getting some shape, some non-infinite slope there. One wishes that cantilevers could be all things, meaning that you could use it to get good images and also good force curves, but that's one of the main dilemmas of AFM is what you gain on one hand is usually what you lose on the other. There are groups of researchers around the world figuring out clever ways to get around this in using high-frequency excitation of the sample to look at the material's properties using a weak cantilever and exciting that cantilever at frequencies higher than its resonant frequency. Then all sorts of interesting things start to happen. I'm afraid that's beyond the scope of what I'm doing here, but it might be the subject of an advanced lesson someday. In summary, for the cantilever, think about what you want to see in your force curve, and then use a cantilever just stiff enough to see that, but no more, so as to keep your images as accurate as possible. And now the tip. Here's a sketch from lesson 17 where I showed you the three basic shapes of tips: the cone, the pyramid, and the sphere. I'd like to add that as far as force curves are concerned, well, in general actually, that your dilemma is now a choice between robustness and resolution. The fatter the tip, the more it will last, but the worse resolution it will have, be it for imaging or for force curve measurements. There is progress recently on coating tips with diamond films, but of course those are more expensive. I'll also add that one thing to be careful of is the strain that you induce during a force curve measurement. Most contact mechanical models do not go, or they do not apply above 15% strain, although some researchers do report 30% strains still fitting those models. So if you do want to indent a certain distance, make sure that you use a tip radius large enough such that the strain is not too big. And the strain is approximately equal to 1/4 the square root of the indentation depth over the tip radius. And finally, watch out for symmetry. As I've mentioned before, cantilevers are often inclined at an angle of repose, and here you see that a conical cantilever would make an asymmetric indentation. And so in that sense, it's nicer to use a sphere where it doesn't matter which angle the sphere comes down, it will still be making a circular contact with the surface. However, despite the circular contact, the force will still be at a non-normal angle, and depending on the material, that may or may not be important. Oh, one more thing. The tip selection and the cantilever selection are not independent. Let's say you've been using a conical tip and a 1 Newton per meter cantilever. And then you decide, oh, I should really be using a spherical tip. And you might think that a Newton per meter cantilever would still be fine. Turns out it's not. Why is that? Well, the interaction stiffness, as we'll see later in the course, is proportional to the square root of the tip radius. So by having a big tip, you will be making stiffer contacts with the surface, and this probably means you're going to have to go up in cantilever stiffness, proportional to the square root of your change in tip radius. In summary, for this lesson, I've talked about probe and tip selection for force curve acquisition, and also how those choices are related.